Okay.
So I feel like it's really like for my question is really simple. Where he did the 70 divided by 10 is 7. Where did that 10 come from? Is that the 1% of 1,000?
No, no. Oh, bummer. This is okay. I'm going to use I'm going to draw on the screen with my mouse. Okay. So, okay, so first of all, let's look at this. So on the left-hand side, this is a cumulative probability of in this particular case, how many correct predictions were generated. And so on these two here, you're looking at these two curves. And basically, if I draw, oh, sweet. Haha. Okay. So there's the first one. That's the first decile. This is the second decile. And then we can kind of draw this over here. The first one crosses over here at 70. 90 over here. Let's do 10. It would be really nice if these decile charts already had these things on it. And I'm going to do the same thing over here. Oops.
Did we lose Jimmy?
I think so.
Yeah, I don't know when he dropped, but he did.
Oh, you know what? He said the meeting session ended for him. So he will call it a night.
Oh, what?
Yeah, he just put a message on the chat like 10 minutes ago.
Oh, you can see that?
Right when mine dropped.
Yeah, like shortly after yours. And he said the meeting session ended for him. It's on our study group chat.
Oh, weird.
Oh,
It's
I just
super
saw it.
weird.
Yeah, my machine just like it just totally reboot. Okay. So let's look at this here. So, okay, so first of all, what the decile chart is telling you is like, what percentage of the correct predictions do you get per number of cases that you look at? So for this first one, in the first 10%, it says that by using the algorithm, you can find 70% of the positive cases by looking at the first 100 results. So if you take your data set and then just and do all your predictions and then sort them by predicted yes or no, and you just took the first 100, that 70% of those first 100 are going to be correctly classified. So if you're looking for if you're looking to get 70% of the value of the predictive value out of the data set, you can do that only using 10% of the cases. So let's say that you needed to send out 100 letters and each letter cost $1. It means that you could send out 100 letters and get 70 correct things using the algorithm versus just random guessing, you'd have to send out what, 710 items to get the same the same positive, you know, the same number of the population that you wanted to 70. I don't know. Have I described that right in words? Does that make sense?
That makes sense to me.
Victoria and Ben?
Yeah.
Okay.
Yeah, it's just the better than chance multiplier.
Yeah, yeah. So this is what the lift chart is telling you. The lift chart on this side, the graphical one, is basically telling you, like, you know, you get to 90% of the things that you want to see, you get after 500 cases versus having to be over at 900 cases. And so the y-axis is the cumulative probability, not cumulative probability, but the cumulative actual when sorted using predicted values. And so when you have a number when you have a curve that's just kind of tracking a little, let me do a different color. If you have a curve that's kind of tracking a little above this, it means you're barely beating the line, you know? And if you have something that does this, something really weird is happening, because sometimes it's better, sometimes it's worse. So you don't like any of these that go against this red line. When it's clearly separated from the red, that means you're doing okay. And so you can ask yourself then, like, you know, if I'm looking to get a 90% response rate, let's say these were mailings to come out, and how many people do I need to email to get a 90% response rate? Well, using the algorithm, you have to email 200 people. Using random chance, you have to email 900 people. So that's how you read how well the algorithm is performing using the lift chart. So now, which one is better, and what do these 7 means? So if we look at the distance from where this thing crosses, so here at 10%, we have 10 cases. We have 10% of the cases. So at 10, we have 10. And this thing here crosses the line almost exactly at 70. And that equals 7. So you can see here, that's our 7 that we get. On this one here, now we're looking at the change from here to here, which is again 10. And it's not 10 for every chart. Like, there are some where the prediction is really low, and so this might be 0, 1, 2, 3, 4. So you really do have to look at the x-axis, at the y-axis and at the x-axis.
So the 10 is actually the y divided by x.
The change in y divided by the
change
in x.
Okay.
Yeah, so here on this one from 20, we went from, so we were already at 70. And here we went from 70 to, I don't know, what is that, 80?
83.
83, sure. So that's 83. Okay, this is really hard to write using my mouse. 83 minus 70, which is 13. My iPad is updating. Which is
Your handwriting is great, Mark. Don't worry.
Yes. This is pretty amazing.
So this is 1.3, right? Which is about what that one is.
Okay. So that is as well the change.
Yeah, exactly. So
okay.
First decile, you got 7 times a better, like 7 times more actual correct predictions using the algorithm than using the random chance line. And in the second decile, you improved the algorithm by 1.3% chance. So in using these cases, you know, you got 10 more yeses, but in using the algorithm here, you got 13. You got 13 more.
Mhm.
So most of the benefit of the algorithm happened in this first case right here. And now in all of these right here, basically after those first 20%, all the rest of these here is basically now you just have a line that's as good as the algorithm. So the algorithm here is getting better by this amount each time. And your line is getting better by that amount each time, right? So this means here, one is exactly doing, like this slope here on the line is 1. Or I should write that here. This slope here is 1. And so in the 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th decile, you're actually doing worse than the algorithm. But you don't care about it because you sucked out all the good ones already here by the time you're 20%. All the rest of these, there's nothing left for the algorithm to get. And so what it means is like somewhere in your data set, like this is logistic regression, right? So somewhere in our data set, and remember the logistic regression is a probability between 0% to 1 to 100% with a cutoff at 0.5. Kind of coming through here. And we know we can change this number. We can tune that, but ignore that for now. So these first 70% were probably the probabilities that were really close to 1. You know, those might represent 0.8 to 1, or maybe 0.9 to 1. And I'm just guessing. I'd have to actually look at the probabilities of each one, but and these here are, you know, maybe the ones that are closer from 0.7 to 0.9. So they're a little hard to tell apart from the ones that were clearly a 1 versus the ones that were closer. And right around here is like, at this point, these are the ones that are really hard to differentiate from the other ones. But it doesn't matter. You've already gotten, you know, 80%, 85% of the actuals in these 2 deciles. So the reason you want to do this is you want to say, look, if I use my algorithm, I can be really cost efficient. I can get the same result out of 200 cases that I would have by emailing 800 people or 850 people. And so now then, comparing the two, if we look at this one, so this one here is again 10 on the bottom because the actual case, it's the same data set, nothing changed. And here on this one, wow, that's interesting.
I think that was a 75, right?
Yeah, I think he's marking as 75.
Oh, right here. Yeah, okay.
Yeah.
Yeah. Okay, I think that's actually right. I think if you look at where this line actually crosses, it is right about here. Right?
Mm-hmm.
This blue line kind of covers it, but you can see the dark blue coming through there. Right?
Correct.
So it did cross there. So that's 7.5. Which is, you know, 7.5 over 10. So the way you compute the decile chart, so if he were to say, like, if he gave you an ROC curve and he said which decile chart matches that ROC curve, you're going to come in here and you're going to literally do what I just did, delta X over delta Y. So that, or really you're looking at where was the y at the first decile, where was the y at the second decile. Sorry, where was the y for the average for the red line? Where was the y for the line of the algorithm? And y algorithm over y red line is your decile chart here. And again, on this one here, you can see that most of the value was captured in these first two deciles. So if you get most of the things you're looking for, which are the ones, most of the correct ones you get in your first 20% using the algorithm, as compared to just randomly selecting. Randomly selecting from the data set. And so now when he asks which one would you use, well, if everything about these two algorithms is equal, in other words, you've done your regression, you've looked at your accuracy, you've looked at your confusion matrix, you verified that you don't have any of that garbage where like everything's predicted as a 0, that these are actually two valid things to compare. And you're asking yourself, would I rather pick model 1 or model 2? Well, this one performed better in the first 10%, so you pick that one. That's all it means. Now, what
So you always want to look at the first decile, first decile.
In general, so you want so you expect a well-behaved model, you expect to do something like this, you know, where they're doing that. If you have a model that does this,
It can go negative?
yeah, it can go negative. If the line is under here, it'll be negative.
Oh, okay.
I guess it wouldn't. Maybe it can't go negative. Maybe that's wrong. You can't go negative. It would just be less than 1, I guess. I guess it doesn't go negative. I think you're right. I think I'm wrong. It can't go negative. It cannot go negative because it's a cumulative probability and you can't lose probability. Probability always has to be greater than 0. So it cannot go negative. You're right, Annie.
Oh, okay.
Yeah. Okay, so ignore that. It does this. You know, so if you have an algorithm that does this and another one that looks like this, which one would you choose? So this is the part that so the way Andy was describing it, if this one here, if this is X and this is Y, if X is greater than Y, you choose X, right? But I would look at it like there's something really weird going on in this model here. This one looks like I expect. So I'd rather pick this one because I think that it's a better, like something's weird is happening over in here. Like, I don't know what it means. I guess we could probably reason it out. What does it mean? I guess what it might mean is there's a good set of numbers which are clearly distinguishable from, like, I did this with you guys, didn't I, of the two curves, of the separation of the curves?
And the crossover.
Yeah. Did I do this with you?
Yeah.
Okay. Sorry. I do this with a couple of people. I forget yeah. So it means that, like, for this first decile, these two were really separable, right? And remember, you have these X's, these X1s, X2, X3, You know, if you can imagine, there are these numbers, these columns of data. And somehow on the first 10%, when you look at all these guys, you can really distinguish them quite well. And then when you look at the second decile, if it goes down like this, down to here, it means that for some reason, those second numbers had combinations of these variables that all of a sudden looked like I had a really hard in telling them, I had a really hard time in telling them apart. And then on this third one here, and let's draw our, this is our one right here. I'm gonna just arbitrarily draw the one here. That's one. So here on this one, all of a sudden we got better. And on this one, all of a sudden we got better. So for some reason, when these things were rated and sorted, however they were, in the first decile, I had clear separation. This and these two here, I had not as good. This one here got a lot better. And on this one, I was way worse than the first one. Like, you expect a well-behaved model to look like this curve. But if you had a model that looked like this, which one would you choose? Well, here's probably the answer. If you were only going to send to the first decile, you would pick this model. Sorry, you would pick this model if X is greater than Y. But if you were gonna send to the second, you know, to the first 20%, you may not like this model at all. You may prefer this one. I'm trying to think of a scenario like, I don't know, let's say you had to let in 200 people into an event, and you're trying to predict whether they're a terrorist or not. And, you know, in this model here, you're always able to predict whether they're a terrorist up to 200 people. So you'd say, yeah, I'm going to pick the model where I can definitely predict people. Here, I have to let 200 people in, and all of a sudden I do really bad here. And I lose my ability to predict. So I'm not going to let people in. I'm not going to use this model. I don't know if that's a good example, because then like I would ask, well, why don't you just then don't touch any of those and just go use these people or these people over here. And I don't know, that's, I don't have an intuitive sense enough on these decile charts to know to answer that. But anyway, what he said was, look, this first column, first decile, you pick the one that has a higher multiplier over the average. That's how you can tell which one is better. My guess is, in general,
Is it the greatest result you get with the least amount of effort?
yeah, that's probably, yeah, I think that's a great way to put it. And it might be that in the second one, for some reason, you know, like you go through an area where you're just not able to get that much information, and then all of a sudden you pick up again. You know, like, I guess that's what this means when it's 0 on the second piece. It's just like this curve goes up, and then for some reason it flattens out, and then it keeps going up again. So maybe you don't throw away this guy. Maybe you really do like it, you know? So this curve here. So another way of looking at it, here's probably a great quiz question if I were him. Can you reconstruct the ROC curve using the decile chart? So if the decile chart looked like this, which ROC curve is it? That's going to be a curve where this here, if this is 7, where it goes up 7 times over the line, So this distance right here is 7. And then it flattens out and then it goes up again. You know, so you could probably, just given a decile chart, pick what the ROC chart is.
Mhm.
And so if you had a chart that did this, 1, 2, you know, like that, then you'd expect to see a chart that went something like this, you know, and then flattened out above this line.
Makes sense.
And then, yeah, and so then these KNNs then, like, this is really, it's just, it's another method. It's trying to group them in n-dimensional space. And the K is how many neighbors do I need to look at close to me? Am I looking at only 1 neighbor, 2 neighbor, 3 neighbors? And I think when you look at this K chart, when you look at the MSE, or any of the errors, you have your K of 0, 1, well, not 0, but you know what I mean. You're going to see something like this. And you pick here. You pick at the bottom. That's your best K. If it got, you might have this where the more Ks you get out, the worse it is. And you could also have this where the more Ks you pick, the better it is.
We don't have that chart as part of solver, analytic solver.
Yeah, well, so you don't have the chart, but you have the data, so you could create it, right?
Okay.
So what happens if I change pages now? Yeah, this is what he's talking about. Oh, no. Okay, let me zoom out. Awesome. I got notability is so much better.
That's what he was telling was the issue with his thing, why he had to have like 50 different screens, because it didn't save on like the screen. It just saved on like over everything.
Yeah. Okay. All that's gone. It's forever gone. Never see it again.
Except in the recording.
Yeah, exactly. And I am recording, right?
Yes.
I hope so. I can't see.
So long this is shared with Nina and not like to 30 some other people, knowing that, you know, showing that I am not understanding this to 5 people is very different to 35 people.
Oh, I think the more important, so A, don't worry, everybody's in the same boat. And B, like, at least you're, I mean, I don't know who I would rather be, because if I say something wrong, like I've just screwed 35 people. I'm a lot more nervous than you are.
I never thought of it that way though.
You got this, Mark. I feel like, think of us as your crash test dummies.
Yeah, I know. Yeah. See?
I'm the 0 of the dummy variable.
Okay.
Say that you're 1 and you know it.
So here, like when we look at this on this K here, when you look at the misclassification, you can imagine as you plot, you know, if you, so you could just grab these in Excel and plot them, K versus your misclassification, and look at where it's lower. And then, like, I know you asked, you know, you can't really tell what it's doing. And that's the thing, like, yeah, this is a completely different way of analyzing it. It's an n-dimensional space. It's not anything our human brains can wrap around, but the math seems to work. And in such a way that the results from the KNN are almost as good. Like doing this crazy mathematical analysis, you have something that's 95% accurate And this one here is also 95% accurate. You can explain this one, you can't explain that one. That's okay. Like, that's welcome to data science. People came up, like, people just had crazy ideas and said, hey, what if instead of trying to predict based off of these characteristics and how they relate to me, what if I just look around? And what does looking around you look like in n-dimensional space? Oh, well, you know, you pick the 4 people closest to you. Okay, well, let's try an equation. And then all of these things here, all of these maths have something called a cost function associated with it. They're all optimizations based off of that cost function. So in the least squares method, the cost function is the square of the distance to the average. It's x minus y squared, x minus x average squared. That's the cost function. You're trying to minimize that. And all of these other ones have basically cost functions that are all trying to minimize. They're just not as easy to explain as linear regression is. But don't sweat not being able to explain it. The more important thing is being able to recognize a valid model and how to compare them. And so this is why, like, when we were doing the first problem in linear regression, I said, you know, here are the 5 things you look at. And they're always the same 5 things. And that's basically what's happening here. Is ultimately, it's just like you say, I'm not going to understand any of the math that's happening beneath it. It's very hard and complex. Even people who have PhDs in data science can't explain the math. But you know, you look at that accuracy, you look at that specificity, you look at the recall, you look at the F1 score, and if all those seem reasonable, then you pick the best one based off of whatever metric it is you choose. And it's really, at this point, it's more about recognizing a model that you want to reject because it's a bad model than it is about, you know, necessarily picking, well, that's as important as kind of being able to determine which is the best one that you want to pick. You have 3 or 4 different numbers you can choose. And some of them get better, some of them get worse. Yeah, that's just kind of life.
Hey, Mark,
Yeah.
since you are doing another session tomorrow, I don't want to ask more questions, and we can always wait because we're not covering this.
Because the thing is, the things that I don't know how to explain, I'll look it up between now and tomorrow. And so I'll be able to give a better answer tomorrow.
Mm-hmm.
It's not like I prepped for this, you know, I'm making this shit up.
No, I know. We wanted to give you a break.
Oh yeah. No. I like the more questions I'm asked, the better it is, because I want to have the answers to help people. So if I don't know something, I can go look it up. Like I meant to go look up the decile thing, but I didn't. But I think I can puzzle it out. Actually, I did look. There weren't any good answers. But I just Googled it. I didn't see an answer that was worth reading. So I walked away and I didn't come back to it.
Thanks for the explanation. That actually helped me a lot. Because I was like, where do you get these numbers from? It's so magical.
Yeah.
But your step-by-step explanation really helped me.
Okay, good. Yeah.
But you know, like I know the error is technically lower in KN versus the logistic regression.
Well,
but it just seems, yeah, but it just seems like the area, I mean, like my understanding is the greater the area in between the what do you even call that line? The cumulative actual?
Naive. You said naive.
It's actually called the area under the curve.
Yeah, so like the area under the curve is greater is better, right? So isn't the bottom better? Like it's just so subjective.
Yeah. Well, the bottom one is the one that you would pick. Oh, you mean
based on the error? Because he said, oh, if you look at, like, I think his sentence was, you know, based on the metric you're using, right? Like if you're looking at the error, then you would pick the top one. But if you're looking at the decile chart, then you would pick the bottom one.
It's true. So if the answer were, if you were asking, you know, I want to spend as little money as possible and get the most benefit out of, like, you know, out of this algorithm as possible. And if you only wanted to spend $100 and you wanted to get the highest yield on that $100 as you could, and it cost you $1 for each case, you would definitely pick this first one because it had a 7.5%, you know, it had a return of 7.5 times instead of a return of 7. So it all depends on what's the question that I'm actually trying to answer. If the question was, I want the model that gives me the best prediction overall, like, you know, let's say it's cancer detection. Well, you pick this model because it has a lower error, and error means a lot to you in cancer detection. But if you're trying to pick who you choose to send an email to, you probably pick this one here because you get your most benefit out of the first 10% of the population, and it does less well on the others. So it really does depend on the question. Like, you know, what if this model was 90% accurate, you know, or let's say this model was 99% accurate, and it, you know, like this curve here, we're at the back. You know, this decile here, we're over here. Like, which model would you choose? Well, again, if it's cancer, you probably pick the one that just had the highest percentage. If it were money, you definitely don't want to burn through 80% of the people to get no benefit before you get that last 10% benefit, even though it jumps you up 90%. But in all honesty, if you got a model like that, where this were over there, I'd probably just throw away the model anyway. Just said, like, this is garbage. I don't know what happened, but I'm not trusting it. Because I don't know why the biggest gain would happen at the very end.
Yeah, I was gonna say if the biggest gain is at the end, then wouldn't essentially that means your curve is under the naive line?
Yeah, that's a good point. If your model is all under 1, yeah, it would look like that. That would be the worst possible thing. Yeah, so you would definitely throw it away. I don't know what.
Okay.
Yeah,
This is great.
that was a very good point. But that's, like, unfortunately, so this is definitely true. Like, which model do you pick and why do you pick it? That really is there's no satisfactory answer to that. And I'm telling you, data scientists people will really get on each other about why, you know, somebody says, oh, I'm picking the lowest error. Oh, you're an idiot. You should be picking the highest decile. You're just like, peace out. tell me which one. Tell me which one you want. Or you say, like, I'm going for cheapness here. I want the one that's cheapest to execute. Which one is it? Like, cheapest to execute over 80% accuracy. Tell me which one to use, and then they'll tell you that. Because these things ultimately can be tied back to numbers, right? It could be that you have a model. Let's say you had a model. Let's say you had let's say you had a model with an X1, an X2, and an X3. And one model had 90% accuracy. And this model here had 80% accuracy. And let's say that this model here used these two variables, and this model here used these two variables. And let's say the cost of obtaining this variable was $1 million per item. This variable was $10. And this variable were $50. And you have to make a decision for your organization. Do you pick this model that gives you 90% accuracy where data costs you $1 million to collect? Or do you pick this model with 80% accuracy where the data costs you, $50 to collect? I don't know. What do you care more about, accuracy or money?
That's a business decision.
It really is a business decision. And that's the thing, like you have to weight it. You don't know. But this is kind of what all these things come down to. And so what do you use? Do you use this decile or do you use this accuracy? It all depends on the business decision you have to make. And that's kind of the key, that what he's pointing out here, maybe that he did by tying it back to individual mathematical metrics instead of to business decisions. But ultimately, you would pick the metric based off of the business problem you're trying to solve. So like I said, coming back to it, if it costs you $1 per case to send something, you use the one that gives you the most economic benefit for the cheapest amount of money. If it's cancer, you go for the overall best, prediction rate. And that's when you use which one. How do you know whether to use the KNN or logistic regression? There's no analytical method. There's no closed form solution that you use. There is a closed form whether you use logistic or linear, whether you're classifying or not classifying. But otherwise, you run all of the models. And if from a business, if you're looking for an 80% accuracy and your first one gives you 80% accuracy, do you go look at the other 5 models? Probably not. You probably just call it a day. Or maybe you do, maybe it's, anyway, it all is about business context. But ultimately, like you'll have data and somebody will go run 10 different models on it and they'll give you the top 3 accuracy with trade-offs, tying that to business decisions, and then you kind of decide which one you want to use. Pure data scientists, though, like people who are doing AI and ML research, they're typically the only number they care about is this accuracy. All right, give me another question. I'm warmed up now.
It's time for you to go to sleep.
I feel like I'm running out of questions on this one.
Yeah. I almost wish that his test is a little more closer to his instruction, instead of like we're getting tested on something that was taught like 2 weeks ago. And I'm losing my memory on those material.
Yeah, well, and also, this material is new for a lot of people, right?
Yeah.
And so it's tough. You have to both learn a new language, learn a new way of thinking about things, and understand which things are important and hold on to what's important and which you're then quizzed on, right?
Right.
So yeah, I feel you. It's a challenge.
Yeah.
And so what he really wants is he wants you to have this level of understanding. And you guys are already, like Amy, you're spot on the being under, like it can't be negative, and these are under if these were all zeros, it would have been this curve here. Like, so you guys, you have that understanding. You're picking up on the important things.
Oh, can you explain more about success class and success probability? I feel like right now we've just been defaulting to 1 and 0.5, but I don't really know when we would change that.
Okay, so success class is which thing you're trying to predict, basically. 1s or 0s. And so he talks about one hot all the time. I don't know, you'll hear it the next time he says it, a one hot.
The one hot encoding?
Yeah.
Oh, okay.
One hot encoding. So one hot encoding is a 1 or a 0. It's just shorthand, what people started calling these. The success class is 1 by convention, and it generally has an answer of, yeah, I mean, like the dropped in our example was a 0, right?
Oh, yeah.
I don't know why I'm writing this out. Dropped was a 0. There's no, I mean, probably in that example, drop probably should have been 1 because we were trying to predict 1. But a lot of times people just use like a negative connotation is the 0. I don't know. I mean, one of them is 1, one of them is 0. You pick and you just move on with your life. It doesn't really matter. But in general, the positive thing that has a positive psychological feeling, it generally tends to have 1 assigned to it, I think, just because people are people.
Okay.
But if you were to try to think about it, if you're trying to predict drops, you probably want your drop to be a 1.
Oh, okay. And then because it's usually like heads or tails, so that's why it's 50.5 probability.
That's right. Yeah, that's exactly right. So your cutoff of 0.5 is because, yeah, you're starting off with the default of 50%, right?
Like a fair coin.
Yeah.
Okay.
So now the question is for you, if you have, remember, these are false positives. Sorry. Okay. So a 0, 0, it's actually a 0. You predict a 1. That's a false positive. And this 1, you predict, it is actually a 1. You predict a 0. That's a false negative.
Mm-hmm.
So the question is, which of these here is more dangerous to you? So for instance, in the predicting of cancer, right? Which is more dangerous? A false negative, right? Because you've been given a clear bill of health. So false negatives are really bad for you. You're going to tune this number so that this false negative becomes as low as possible, so that this false negative drops to 0. That's why you would tune this number, is to adjust these two. If you have a 0, and maybe you can adjust it so that these are both 0, but remember, that's what this ROC curve is here. When the ROC curve looks like, this, that's when you have perfect separation of the 1s and the 0s. And that's when your false positives and false negatives are both going to be 0. And so then there's generally a trade-off now. When you don't have a perfect prediction, when you try to decrease the false negatives, your false positives get worse. And when you try to decrease the false positives, the false negatives get worse. And that's essentially what you're tuning this number for, is whether you want to minimize or maximize, well, whether you want to minimize that or that. But if there happens to be a percentage, a cutoff value that gives you a perfect fit, then that's also good. So a lot of times what you might do is, this is something you would do in Python, and this, in a real programming language as opposed to Excel, is you might run a script between, say, 0.3 and 0.8, and look at your false, plot your false positives and your false negatives, and have the algorithm tell you which one was better. Like, hey, it turns out when I did 0.65, when you did 0.65, that my false positives were minimal. So that's the value you would use. And now if you were tuning this cutoff thing right here, if you were going to be tuning your model and trying to pick your right value, would you want to use 2 data sets, like your validation, your your training, validation, and test? If you were trying to tune this number, would you want to use 3? Would you want to split your data up, partition your data into 3 pieces or 2 pieces? Question for you guys. Hello?
Is it 2?
It would be 3. Because your first piece, the training, gives you your model, your training gives you this data. The second one, the second set, lets you create sets of these. So you can pick which of these is better, the first one, the second one, or the third one, all using the same training data. And then the test data is what you use to pick which of these does the best. I don't know if I explained that well enough. First one generates that. Second one lets you generate sets. And then the third one, basically, when you train your model and you get these sets of numbers, you bias your data for this test set. And now when you start adjusting the parameters and you generate this one or this one or this one, you now have biased your data towards I'm just going to call this lambda, towards the parameter that you're tuning. So in the example, in the K1, you're biasing this one for the K. The test data is an independent, untainted data set that you're never contaminating by using it to make decisions that involve choosing coefficients of the model. I don't know, does that make sense?
That does make sense, because I think I was getting confused remembering what he said. Like some of it, you just have 2.
Yeah, so in linear regression, you only have 2. You only really need 2 because there aren't, is that true? So in linear regression, if you were going to be trying to decide whether you wanted a model to be X1 and X2, or whether you wanted a model, you were going to try to choose between X1, X2, and X3, you might use 3 sets.
Okay.
So you can always just use 3 if you want to. There's no harm in using 3.
Right.
It's more of like, when can you get away with using 2? Well, you get away with using 2 with using just a training set and a test set, when you're just going to run the model and you're not going to tune it. If you're going to tune the model, you generally want to have a test set that's independent.
I was actually going to ask, like, is there any time we would go above 3? Is it just when you have like large sets of data that you want to build multiple models, maybe independent of each other?
Yeah. So in practice, if you had, let's say you had a model that had 1 billion records, and let's say you couldn't fit all of that data into a computer, you might actually split it up and average them so that you could actually have, you know, different sets that are consumable based off of the resources available.
Okay.
Otherwise, I don't know why you would split it up into more than 3. It would really be like you had to run the data on 3 different computers, and so you were gonna try to do it. So a lot of times what happens is, like I said, let's say you do, let's say you have data sets like we were talking about where you split these up into 10 chunks. And so what you might have is, you know, you'll run a test where this one here is the validation. And this one here is the training. And then basically you'll run this, you know, you'll do 10 times where the validation move, where the training, you know, you use this one for training, then you use that one for training, then you use that one for training, then you use that one for training. And same thing with the validation, it bounces around. And then you basically, you take all the parameters and you average them out. And I don't know what the parameters for KNN are, but for linear regression, you know what they are. You get beta 1, beta 2, beta 3. You would literally just take an average of all of them. And there's even more sophisticated models than that. Like really, people go crazy with different ways of combining things, trying to improve this overall accuracy number. So the short, I don't know if there's a short or a long answer to your question. For what we're doing, you really only need to worry about 3, but yeah, people do split it up more, but generally it doesn't have anything to do with the training and the validation and the test are independent from each other and you're trying to pick different things. It has more to do with you're either doing that to try to drive up your accuracy or to reduce the training time on a large data set. And by large, I mean more than will fit into a single computer. So Facebook or Google large, you know.
That's pretty cool. Thanks, Mark.
Oh, you're
Oh,
welcome.
thanks, Mark. Now we warm you up for tomorrow night.
Oh, I'm warmed up, yeah. All right. Well, this
All right.